Hello, come on in. Ask me any questions if you have any. I'm here a little bit early in case anybody has any questions. Waiting for my iPad to turn on. Date is the 20th. Hey, Shonda, how you doing? All right, looks like we're ready to roll.
Hey, okay. Yeah. Are we starting early today or am I late?
No, I showed up early just to in case anybody had any questions. This Gauss's law is supposed to be somewhat easy, but it's the understanding portion is not so easy. So I just want to make sure I got here early.
Yeah, it was a little weird, but it's okay. Yeah. I don't know. I missed class last Thursday.
I saw you weren't there. Oh, that's right. You weren't
Yeah,
there yesterday either.
yesterday?
Oh yeah, that's right. I forgot. Yeah, I keep forgetting you're in the day lab, but the night lecture.
Yeah, but I mean, last week I just totally I've got a really bad cold. I just took some medicine. I don't know if I slept through the class or what happened. But I sent you an email because even though I show up in this
Right.
class, I can't access the recorded Zoom meetings because they took that off the dashboard.
Oh,
So
gotcha.
you usually post these, so I sent you an email about can I get a link because the dashboard link that I have is for the other class. I just turn all my
Yeah,
homework in a day early and
I got
stuff.
that
I don't
email
know.
from you, but it was like minutes after I'd emailed everybody and told them where I'd posted it. That's why I thought it was just something you
I
didn't realize I just posted
I,
it.
I maybe I you know what? I thought about I'll look at that
Yeah, go to
and
my
I'll
YouTube
just see.
channel.
Was the link in the email?
No, well, I might have, but I don't think I did. But if you go to my YouTube link and just do a search for that particular date, you know,
Okay. Yeah, I'll
O
figure it
two
out.
one five 2024 or something like that, it'll pop right up.
Oh, two. Yeah, I thought that you did something like that, and then I went to go check on the algebra what happened. I had three tests back to back Friday, Saturday, and Monday on
That's
like
a lot.
linear algebra, probability, and statistics, and like uh some other math class. I don't know.
Yeah,
You
exactly.
know what I thought though, after taking linear algebra, which is not that bad after having had physics and calculus 3 and
Uh-huh.
differential equations, that I wish my counselor had told me to take linear algebra when I first started. It would have made life a lot easier. I would have, if they, yeah, it would have just made life a lot easier for your class and multiple other science classes that I had to deal with vectors in. A lot easier. I
Tell
don't
me
know why
something
they
about
don't tell you to make that. I don't know why they don't advise linear algebra as a prerequisite to a lot of these classes.
yeah, tell
Linear
me something
algebra is
about your
just the
linear
vectors.
algebra class, Shonda. Does it have you had to do proofs like proofs that such and such is a linear vector space or any of that kind of stuff?
We're just gonna do that now, and then we get into eigenvectors and all that stuff. But this unit is the proofs of what matrices and vectors are and stuff. So
Gotcha. I was just
yeah.
curious. There's a linear algebra that's sort of a computational level where they just teach you all the cool nuts and bolts of matrices and all that stuff. And then there's a more there's a bunch of different variations, but then there's also a version where it's much more sort of esoteric, and you start off with just some simple matrix stuff, but you go into vector spaces, defining an algebra, and you end up using some calculus and stuff like that. So I was curious what kind of
Yeah, that's the one we're doing now. It's more for engineering and physics students. So we're doing the
Cool.
proofs of this different stuff. So I'm about to get into all that stuff. And I'm like,
Yeah,
this would have been really
it's
nice to know for
it's
everything
absolutely
else. I could
great to have for physics courses and
I wish
engineering.
I'd
There's
had
so many
this
things you can
a
do with
year
it.
ago.
Yeah.
Yeah. Yeah. It's just, yeah. But they didn't tell me. I took everything in Bolt's variable calculus, and then now I'm taking linear algebra. I'm like, I wish I'd had this before I took the anyway. But that's all.
Yeah.
But no, the Gaussian stuff, it's I'm gonna listen to the lecture, and I gotta go back and look at your other lecture from last week. I'll probably get to that tonight or tomorrow after lab. And then other than that, I'm just making it through. But just familiar with some electricity from
Right.
other electrical training I had. So,
Well, that's
but the
cool.
class I learned a lot. Learning a
Yeah.
lot. Is it?
You do. You get a lot
Yeah,
out of it.
it's a
Well, I guess
lot.
we'll go ahead and get started.
Okay, good
Uh,
talking. All
yeah,
right.
the linear algebra is a good thing, though. And there's so many cool things in my solid state physics class. We had to create a 100 by 100 matrix and then diagonalize it. And then when we were done, it was this big project. It was like a midterm. And when we were done, he gave us a printout of a 1970s Nobel Prize winning article that we had basically just finished doing the same work of. But that poor guy in 1970 did it by hand. Pretty crazy stuff. I'm going to go ahead. We're talking about Gauss's law now, and I want to remind everybody that I do have some videos. I want to say that I actually linked some of them in last week's and maybe even this week's module, but definitely check last week's because I think they're there week 6 as opposed to week 7, but it might be in week 7 where I actually work out the details of what we call a surface integral. So that left-hand side of Gauss's law, which is the integral, it's actually an integral with a circle on it. And the circle on it just means, hey, reminder, you're using Gauss's law, and Gauss's law only applies to closed surfaces. So they put that circle on it to remind you that the integral has to be over a surface that has a clear inside and outside. Meaning if you're in the inside and you want to go outside, you've got to cross a boundary, specifically a side. So that's what that's for. But the other part is it's the integral of E, the electric field, dotted with a dA vector. And that's a whole process in itself. But basically, what it involves is you have a vector field, E, and you have a differential area vector, dA, that is defined to be perpendicular uh, to a minute little area element on each part of the surface of the shape that you have. And you're supposed to, since it's a surface integral, evaluate the electric field, or in this case, any vector field. In our case, it is the electric field, but any vector field that you have to take the E.dA with, that has to be evaluated on the surface. So if you're doing like a square and the left-hand side is at, let's say, y equals 0, then you literally have to take the field, the E, and if it has any variables y in it, you have to put in y equals 0 for all those. Uh, and then, of course, you've got two other variables left, the x and the z. And normally you would handle that with a double integral, and when you do so, you integrate it from the smallest x to the largest x, and then from the smallest z to the largest z. Wow, I keep saying y instead of z. Uh, anyway, so that's a process, and I don't like the idea of giving you these surface integrals with Gauss's law without you having some knowledge. So I've shown you the simple ways with the wonderful Gaussian surfaces that we're doing, but I don't feel right about you guys not having some exposure to actually computing a surface integral. And your book, as well as the homework, as well as the questions at the end of the chapter, does have surface integrals you're supposed to evaluate, but it has very simple cases. So if you can muddle through my examples in my YouTube channel to get some understanding of the whole process that goes into integrating over a surface, then all these other ones would be really simple. So I don't want to spend a lot of time doing that. I just want to go on to doing the examples for Gauss's law. Really, your book's expecting us to spend a day. I'm now going to spend a second day on it. So this should be the end of it. All right, so let me go ahead and share my screen so we can work on Gauss's law. I'm going to treat 3 specific spheres. Uh, and in doing so, I can show you some interesting things. One thing I didn't show you last time, I think I might actually go ahead and start with, which was when we did the integral, or excuse me, when we did Gauss's law for an infinite surface. What we found was that the electric field was sigma over 2 epsilon naught k hat for z greater than 0, and then negative sigma over 2 epsilon naught k hat for z less than 0. So that's sort of an important thing. So I just want to graph that real quick and explain to you why that's important. So remember what we got was the electric field due to an infinite plane turned out to be equal to sigma over 2 epsilon naught k hat for z greater than 0 and negative sigma over 2 epsilon naught k hat for z less than 0. That was the actual output of our Gauss's law when we applied it to that Gaussian pillbox, Gaussian cylinder, or whatever you want to call it. If you actually graph this, it would look something along these lines. So we could actually draw this and say this is E, the magnitude, and say this is Z. And what we get is when Z is a positive quantity, we get a sigma over 2 epsilon naught that actually looks like this. It's got a more or less an open spot, and then it's a horizontal line. And then if I step down to the negative Z, again, it has an open hole and goes this way. This right here is actually a discontinuity. And if you take the discontinuity, which is E positive minus E negative, you would get sigma over 2 epsilon naught minus negative sigma over 2 epsilon naught, which equals sigma over epsilon naught. Well, that turns out to be a physical principle. In fact, it was like one of the first questions that was asked of me in my graduate level electrodynamics course, like literally 2 weeks into grad school. So it's one of those things that's kind of important, and this is an excellent example of it. Basically, what it's saying is that the component of the electric field, let me go ahead and write this. The perpendicular component of an electric field suffers a discontinuity at a boundary if there is a surface charge sigma. That discontinuity is sigma over epsilon naught. Okay. So that's like what we call a boundary condition for Maxwell's equation. So it is a fundamentally physical property that's important to us, but we don't often get to see that much at this level. So this is one case. I'll show you another one in a second, but I just wanted to cover that regarding the infinite plane. So hopefully y'all remember. Of course, Shonda doesn't because that crack baby slept in. I'm picking on you. But hopefully y'all remember that when we actually applied Gauss's law for the infinite plane. If you didn't, of course, you can always look back at the video and hopefully that'll help you. So anybody have any questions on that part and what I mean by discontinuity and stuff of that sort? Another reason that I want to tell you that is until I understood this thing about discontinuities with boundary conditions of Maxwell's equations, I didn't really have much of an appreciation for what we did in statics. When I had my statics course, which was a calculus-based statics course, there was a big part of it that was about discontinuities. In other words, whenever you had a point load would actually cause a discontinuity in the load diagram, and you would actually physically use that discontinuity to calculate it and then use it to figure out something very specific about the load, so you'd know how to, spec a 2x4, 2x6, a 2x8, a 2x10, a 2x12 flitch plate or whatever, when you have a point load somewhere in your distribution. So just keep that in mind when you guys get to your statics, if you haven't already done that, or if you're in your statics. They're probably not going to cover it until you get to the calculus-based statics, or they might just sort of do some hand waving and give you some results. And that will mean, oh, well, that's something I might better understand once I've had the calculus-based version, or once I've looked at it with respect to what Mr. Younger just said or something. Okay. So let's go ahead and start off with yet another Gauss's law problem. In this case, I'm going to actually imagine a non-conducting sphere, and that non-conducting sphere will have a radius r and a total charge q, and the charge will be distributed uniformly throughout. So oops. I should probably stop writing in cursive because I know there's a lot of people that aren't learning cursive nowadays. A spherical non-conductor of radius r and total charge q has its charge distributed uniformly, throughout its its volume. Compute the electric field everywhere. Okay, so that's the problem. We're trying to compute the electric field, and when I say everywhere, I mean I'm considering what is the electric field inside of the actual spherical non-conductor, what is it outside of the spherical conductor as well. And I'll tell you, this in principle could be done with the Coulomb's law integral version that I gave you, but in practice it can't be done because it's just too much of a nightmare to integrate all that. But you'd have to usually, well, you might be able to find some really cool ways of doing it, but generally speaking, you'd have to write code to do it. So in this case, we actually get one that's not quite so bad as far as Gauss's law goes, meaning it's something that we couldn't do otherwise. So what I'm going to do here is I'm going to draw the x-axis, the y-axis, and the z-axis. This is my x-axis, this is my y-axis, and this is my z-axis. Now I'm going to draw the actual object which is supposed to be a sphere. And of course, I cheated using the software's ability to draw good circles. Okay, and this radius right here is R, meaning capital R. Okay, and the total charge is Q, which we've already written that. Now, what I also have to do is, in order to use Gauss's law, I have to actually choose a Gaussian surface. And this is the most important sentence that you need to know in using Gauss's law. So Gauss's law well, I'll tell you when I start the sentence. Gauss's law uses our knowledge of Coulomb's law and our experience in dealing with charge distributions so that we can sort of guess in what areas the electric field points in which directions. Okay. So, for instance, last time when we had an infinitely large plane, which really doesn't have to be infinitely large, it just means in practice, maybe you're 10 times closer to it than it is from you to the edge. That's often good enough. But the main thing is from that, knowing it's an infinitely uh, large plane that is uniformly distributed charge on it, you know that the electric field should be a constant on a plane parallel to that infinite plane. That's sort of the knowledge that you need going into Gauss's law. So here's the sentence that's most important. In doing Gauss's law, we have to choose a Gaussian surface for which the electric field is both perpendicular to the surface and constant on the surface everywhere except for maybe a few places where the electric field is actually more like parallel to the surface. Okay. And again, when I'm saying parallel to the surface, I mean literally like the electric field lines lie in the plane of the surface, and the surface area vectors are perpendicular to those surfaces. Okay. So we have to now choose choose a Gaussian surface that has the electric field as a constant, preferably on all parts of the surface and perpendicular to all parts of that surface. Or if it has multiple parts, you might have some parts where the electric field is in fact parallel to the surface so that the dot product part goes to zero. So what I'm going to do is I'm going to draw a blue Gaussian surface, and I'm going to cheat again. Of course, we're going to have to draw one for R bigger than R and one for R smaller than R. So this is the first one we're drawing. Okay. So that's the one for R bigger than R. Oops. Let me undo that. Let me undo that last thing too. Now I'm going to draw the one for R less than R. Okay. So what we've got going on here is a radius vector little r that points to the Gaussian surface, and of course another Gaussian, or excuse me, of course another line. Ooh, don't know what happened there. Of course another crap radial line is what I need to show this. I'm going to try to erase that spot without erasing everything else. Okay. So this is another radius, little r. So that little circle inside there is a Gaussian surface, as well as this big blue circle outside. So I'll write, oh man, I hate it when that happens. I really got to figure out how to turn that off. Okay, so that's our Gaussian surface. So now I'm going to write our solution. Now, part of the idea is once you've actually figured out what the shape of the electric field is, you sort of make a hypothesis about the shape of the electric field. And I've been formally writing that for the last couple of years, and I like the completeness of it, and I think it's easier to read if you're just looking at one of my solutions. I'm not sure it helps you that much in real time my teaching, but either way, I'm going to go ahead and continue to use it, see what happens. So first off, my hypothesis is is that the electric field E, I suspect, based on my knowledge of Coulomb's law, which, remember, Coulomb's law gave us the magnitude of the electric field, and that magnitude was Q, the charge, divided by 4 pi epsilon naught r squared, and that r was the distance from the charge causing the electric field to the point at which you wish to know the electric field. So if you wanted to look for a surface on which the electric field strength was a constant, you would obviously want to select r equals a constant, which tells you a sphere, and that's why I went with a Gaussian surface that was a sphere. Not only that, you see that it only depends really on the distance between the charge and the actual location at which you wish to calculate the electric field. So in this case, I'm going to say the electric field hypothesis is that the magnitude of the electric field is probably only going to depend on R, and that it's going to point radially outward. Okay. So radially outward, that means to me, because I have experience with these types of coordinates, and I've also given you some things where you can look at yourself to figure out these types of coordinates. But in spherical coordinates, which I'm used to, the r hat vector is a vector that if you take any point in space and you connect that point with a straight line from it to the origin, then the r hat vector will be a unit vector that points parallel to that line you just created, but away from the origin. Okay. So if you think about that, you think about this purple sphere actually having its center at the origin, then you see that everything about this purple sphere has a spherical symmetry. So you expect the electric field should point radially outward at all points in space. And in fact, if you take a concentric sphere, which is what our Gaussian surface is, and put it in the coordinate system, then the electric field will be perpendicular to that surface everywhere on the surface. And because it's perpendicular, that means it's also going to be a constant magnitude. Okay. So let's go ahead now with this. So the solution, there's my hypothesis. Really what's going on here is we're choosing differential area vectors, dA, that are perpendicular to the Gaussian surface. Okay. There's all sorts of neat coordinates and things you could use to find what dA is, but in practice, the best and easiest way, which you probably wouldn't be using if you had this, would be using spherical coordinates or cylindrical coordinates in some cases, and using those with double integrals to calculate what the actual dA is. And here, I'm just telling you, such dA vectors exist, and the fact that they point radially outward is important to us. What they're actually made of doesn't matter. So I'm just going to use things like dA r hat. So here's Gauss's law. The closed integral of E dot dA is equal to Q enclosed within the Gaussian surface divided by epsilon naught. So I'm first starting off with R greater than big R. So I'm starting off with that outer blue sphere right now. And what I'm going to do is I'm going to compute the left-hand side. I've mentioned this to you before. I'll mention it again. Because of what we're doing with Gauss's law in this course, which is usually we're trying to extract that electric field out of that surface integral and use it to find out exactly what the electric field strength is, that can only be done with certain symmetries. And because we're doing it that way, we're not really taking an equation and working it out until you get an answer. You're actually working the left-hand side of the equation to get an answer, work the right-hand side of the equation to get an answer, set the left-hand side equal to the right-hand side, and then solve for the electric field. So I found it's most complete to write out the left-hand side first, then the right-hand side. So the left-hand side is the closed integral of E dot dA. Now, what that turns out to be is basically our hypothesis, E of R times r hat, because it points radially outward. And then I'm going to dot that. And here's where the part comes in where I tell you it doesn't matter what crap dA you're using. In other words, you don't need to know the details of whether I'm using spherical coordinates, double integrals, single integrals, or whatever. All you really need to know is that this left-hand side is going to turn into an area times an electric field. If it doesn't, you've screwed up horribly. Okay, so I'm just going to call this dA vector. I'm going to say its magnitude is dA and its direction is r hat, and that's it. Right? That's the beauty of a unit vector. You can multiply it by any scalar and it gives it a direction without changing its magnitude. Now, because of the nature of this Gaussian surface, we're actually integrating on the surface of radius r, which means on that Gaussian surface. And on that Gaussian surface, the electric field strength should be just plain E of r, and it's going to be a constant. So I can put that out in front as E of r, and then all I'm left with is the integral of dA, but I then have r hat dot r hat, which works out to be just 1, okay? Now, the integral of dA is over the spherical surface. So we're literally saying, hey, what's the surface area of a sphere? So the answer turns out to be just E of r times 4 pi r squared, okay? See, again, we just got a magnitude of electric field times an area. Now I can do the right-hand side. And in this case, the right-hand side super easy because remember, Q enclosed means how much charge is enclosed inside of that outer blue sphere. Well, the whole purple sphere is inside of that outer blue sphere, so the whole charge is in there. So the answer is just Q, and then we divide that by epsilon naught to get the right-hand side. Now all we do is we set left-hand side equal to right-hand side. Feel free to ask me any questions or stop me if you don't understand something. Well, that was horrible. I really should be a little less obsessive compulsive, but I can't be. I could. I just need more medicine or something. All right, left-hand side equals right-hand side. So we're going to say 4 pi r squared E of r is equal to Q over epsilon naught. You can see right now that we can easily solve for the magnitude of E of r, which is what was in our hypothesis. So I'm just going to go ahead and write out the electric field in terms of our hypothesis and say that the electric field is in fact equal to Q over 4 pi epsilon naught r squared r hat for r greater than big R. And that's going to be our answer, at least for that part. Anybody have any questions about that? Okay. Now we've got to do for R less than big R. And this part gets a little more complicated because we've got to figure out what kind of charge is inside the inner Gaussian surface, that little blue one. Okay. So I'm going to say, go back to my blue, and I'm going to say R is less than big R. And what I have to realize is the fact that it's uniformly distributed throughout. So I'm going to go up here and underline this: distributed uniformly throughout. Those words mean rho is equal to a constant. And hopefully you all remember what rho is. In case you didn't, here's the deal. What you can do is say that Q enclosed is either equal to the integral of lambda times dl, or it's equal to the integral of sigma times a dA, or it's equal to an integral of rho times the differential volume element. So that's totally unrelated, of course, to the boundary conditions that I was talking about up there, but I just wanted to show it to you without having to flip back and forth between screens. So that's one way of writing it. You could also write lambda is equal to dq over dl, sigma is equal to dq over dA, and rho is equal to dq over dV. That's another way. So lambda is equal to dq over dl is acceptable. Sigma is equal to dq over dA, and rho is equal to dq over dV. Again, we're talking volume here and area in the other case. All right. So since we know rho is a constant, we can take the actual charge divided by the volume and set that equal to the charge divided by the volume for a part of it. So we know, for instance, the entire charge is Q, and the entire volume of the spherical charge distribution is 4/3 pi r cubed. So that's one of the rhos. Now we can also set that equal to the charge, the rho for the small Gaussian surface. And in that case, we get Q enclosed, which is what we need, divided by 4/3 pi little r cubed. Does that make sense to everyone? Y'all see how I made that argument? And just for the record, I'll say this is all just equal to rho. Now I'll go back to my blue. Now from this, we can see that Q enclosed is in fact going to equal, because I can cancel out this 4/3 crap with this 4/3 crap. And sorry about the crap reference, but I'm a man of many, many impressive words. So Q enclosed is going to be, dang it. See, more of my special words, is going to be Q times little r cubed over big R cubed. So just getting that response is super, super helpful. Now, look how easy this problem becomes. We're going to say left-hand side. And of course, we know that's the closed integral of E dot dA. And guess what? And this is what you should be doing when you're actually taking a test. All this extra stuff I'm showing you is to help you understand. But when you're actually taking the test, you probably are just going to write, oh, this is 4 pi r squared times E of r. And then you're going to write right-hand side. And that's Q enclosed over epsilon naught is equal to Q over epsilon naught times r cubed over big R cubed, like that. Now I can set left-hand side equal to right-hand side. And when I get that, I can see, dang it. Anybody know how to turn this off? Please send me an email or text if you do. Okay, so it looks like it's still working. 4 pi r squared E of r is equal to Q over epsilon naught times r cubed over r, big R cubed. In this case, you can see that the r squared cancels out with all but one of the little r's. And you can actually find that I'm now using the hypothesis again. We're going to say E, the vector, is actually equal to Q times R over 4 pi epsilon naught big R cubed, all that times R hat, and this is for R greater than big R. And that's the actual answer. Notice how nicely the units work out. That R cubed in the bottom is exactly what we needed to compensate for that little r on top. What we also see here, by the way, is the electric field inside of the sphere is linearly increasing. So that literally means if I double the distance I am from the center of the charged sphere, then I double the electric field strength that I'm experiencing. Someone says they think I messed up the R. I don't believe I did, but definitely keep on checking it out. This is what I remember being the right result, so that I suspect it's right. But remember on the part where I said equals rho, when I multiply by r cubed on both sides, that leaves Q enclosed on the right by itself, and big Q and little r to the third power both on the numerator of the left-hand side, and big R cubed in the denominator. So hopefully that makes it. Oh, that's what I mean. Oh, yeah. Definitely I'm wrong in that case. Thanks, dude. Appreciate that. Who was it? Micah? Appreciate it, Micah. I thought you were getting on my algebra, but yeah, I absolutely wrote that backwards. So this is for R less than big R. Yeah. Again, definitely need some help with that. So R less than big R. And if you look, this it happens to be a charge distribution for which there was no surface charge. So if you substitute big R for little r in those two equations, you'll see that they get to be the same answer. So I can actually change this to greater than or equal to, and this one to less than or equal to. And if I actually plotted it, which I'm getting ready to do now, like so, there's R, there's E. This is going to be Q over 4 pi epsilon naught R squared. If I come out here and call this big R, then what we're going to see is the graph starts at R equals 0, E equals 0, and then runs into that spot right there as a linear function that goes through the origin. And then after it gets out of there, it falls off like 1 over R squared. So notice there's no discontinuity in there. Now, the derivative is discontinuous, but the actual electric field is not. So that's why we don't have any, because we don't have any sigma there, no surface charge density, we don't expect a discontinuity. So any questions on that one? Now, I did say that one was a non-conductor. And the reason I said that was to let you know that, remember the rule, if you've been reading your book, you've hopefully heard a couple things or read a couple things. One of the things your book told you was that in electrostatics, the electric field inside of a conductor is always zero. Oh, hold on, Mike. I just saw that you were writing something else. I'll get that in a second. So the electric field inside of any conductor is always zero in a quote unquote electrostatic situation. So if you don't have, for instance, a battery or a power supply directly connected to a conductor so that current can flow, if you don't have that, then you have an electrostatic situation. You might, for a brief second, even without that, have a non-electrostatic situation, but that's just transitory while the charges are distributing themselves as they're supposed to. Because of that, and because of Gauss's law, you can show that, in fact, all charges on a conductor will reside on the outside edges of the conductor. The way you do that, and your book explains this, is you imagine a Gaussian surface that's exactly the same shape as your conductor, but it's just like a single atom within the surface of the conductor. So it never actually pierces the surface of the conductor, but it's always just, maybe a single atom's diameter away from the surface. You draw that Gaussian surface, and since that is in the conductor, E is equal to 0. So if you apply that to Gauss's law, the closed integral of E dot dA has to be 0 because the electric field is 0. If that left-hand side of Gauss's law, the closed integral of E dot dA, if that's 0, then that means Q enclosed has to be 0. So that's your proof that all the charge will reside on the outside edges of the conductor. Okay, I'll go over that again in a second, but let me look at Micah's question. Wait, can you also explain what you just said again? Okay, so what I was saying was in order for me to find the Q enclosed, I said rho for the entire sphere has got to equal rho for the partial sphere. In other words, the sphere that I've enclosed in the Gaussian surface of radius r that happens to be smaller than big R. So that meant Q over 4/3 pi r cubed, where r is the big R, is the rho for the entire sphere, whereas the rho for the partial sphere, the one that's inside the inner Gaussian surface, is Q enclosed over 4/3 pi little r cubed. And that allowed me to solve for Q enclosed being big Q times little r cubed over big R cubed. Gotcha. So, Micah, did that help you? Feel free to write it up there. Ah, cool. Okay, so now I'm going to show you another one, and this will give me a chance to explain a little bit more about what I was saying for the conductor. So this time I'm actually going to compute the electric field everywhere around a spherical conductor of radius r. So a spherical conductor has a radius r and a total charge Q. What is the electric field caused by that sphere? Okay. So notice I didn't say anything about the charge distribution. I didn't say it was distributed throughout. I didn't say it was distributed on the surface. I didn't say it was distributed uniformly. I didn't say any of that. But by me saying conductor, that's supposed to tell you all of that. So that's a whole nother concept that we can put in a question just by wording the question this way, and it hinges on your understanding of the way a conductor behaves. So what I'm going to do is I'm going to draw a coordinate system again, just like I did before, and I'm going to put a sphere on it. And then I'm going to put two other spheres on it, and those spheres are going to be my Gaussian surfaces, of course. So there's my y-axis, there's my x-axis. This time I'm going to draw my Gaussian sphere, or excuse me, I'm going to draw my sphere in blue. And we see why I like to use the automatically correct my drawing feature. Oh, that went badly. I'm going to do all that, get rid of all that thing. Whew, that was terrible. I was trying to make it 2 squares and I got hung up in the middle of it and made it 3 squares. Okay. So that's the actual Gaussian surface, or excuse me, that's the actual conductor surface. It has a radius big R. Now this time I'm going to draw a Gaussian surface. Let's draw it in black this time. So I'm going to draw a Gaussian surface. Dang it, I forgot to get it to draw it nicely for me. So I'm going to draw a Gaussian surface. Let's see if it'll do it. Nope, that was horrible. So, okay, this should do it this time. Yes, much better. Okay, not perfect, but much better. That looks fairly decent there. Okay, now I'm going to draw also the inner Gaussian surface because remember, I'm asked to calculate the electric field. So I've got to consider not only R greater than big R, I've got to consider R smaller than big R. And I'm going to do this one by imagining a sphere of 1 block radius like that. Okay. So in this case, I've got a radius that is little r. And then in this case, I've got a radius that is little r as well. Okay. So what I was saying earlier about a Gaussian surface or a conductor is this. So let me draw a circle over here real quick. I'm going to draw a circle. Let's say, and there I go again, not using my tools. Like that, okay? So if this is a conductor, uh, so in electrostatics, there's no current to be had, and the current would have been caused by like a power source or something like that, and that allows, charges to move around the conductor. The charges will readily move around a conductor. That's the nature of a conductor, but they do that in a transitory and very quick fashion to get equilibrium established and stuff like that. But in this case, we're talking about ignore that transitory period. Now, since we know E inside is 0, we can now make a Gaussian surface, which I'm going to say is roughly there. So this is supposed to be a Gaussian surface. Barely inside. Okay. Now, this little fact, the fact that it's electrostatic, or excuse me, the fact that the electric field inside is 0 says the closed integral of E dot dA for that Gaussian surface is equal to 0. Okay. But this causes Q enclosed equal to 0. And of course, okay, does that make sense to everyone? So the conductor is the purple sphere. And I've chosen to draw a Gaussian surface just barely inside of it. Okay, like literally like a single a single molecule or an atom in diameter or even radius away from the outer surface. And in this case, it happens to be a sphere, but it could be any shape, and you just have to draw a Gaussian surface within that shape that's completely inside. And since the electric field inside is 0, that means the closed integral at E dot dA has to be 0 because you're obviously integrating the electric field dotted with dA, but the electric field is 0, so you get 0 dot dA, which gives you 0. Now, Gauss's law says that flux, the closed integral E dot dA, is exactly equal to Q enclosed over epsilon naught. Therefore, that 0 that you got now says the Q enclosed is 0. Since the Q enclosed is 0, that means all the charge must be outside of that. And you can redo that black sphere all you want to until you get it closer and closer to the surface, but you're always going to still get 0 unless you're outside of the surface. So does that help? Does anybody have any questions about that? All right, so let's start. And I'll do the solution in purple this time. Oops. So again, I'm going to make my hypothesis. And again, I'm using the fact that Coulomb's law says that the magnitude of E is equal to Q over 4 pi epsilon naught R squared, like that. So if I take a spherical distribution of charge that is in fact spherically distributed, about the origin, then any sphere centered on the origin will have a constant electric field on that surface. So that leads me to my hypothesis, which is that the electric field everywhere is only going to depend in magnitude on r, the distance from the origin. Because remember, when we have a spherical charge distribution, the spherical charge distribution behaves just like a point charge at the origin, whether it's all on the outside edge of the sphere or whether it's uniformly distributed throughout. The spherical distribution is always going to act like a point charge at the origin. So that E magnitude is going to be E of R only, and it's specifically the distance from the origin. So I'm going to get E of R times that same R hat that we talked about earlier, which remember, at any point you draw a line from the origin to that point, then the R hat vector will be parallel to that line, but pointing away from the origin. Okay. So now I can attack the left-hand side, and notice I'm slowly doing the left-hand side quicker because we're not supposed to waste a lot of time on that. Me telling you all this stuff is about you learning exactly why it works. So the closed integral of E dot dA is just going to become the integral of E of R hat dotted with, again, you don't care about the details of what the magnitude of dA is, but you do care about the fact that it points in the R hat direction. And then you get E of R, the magnitude, times the integral of dA, oops, no vector symbol there, times R hat dot R hat, which equals 1. And all this, of course, now becomes E of R times the integral of dA carried out over the sphere. Okay. And specifically carried out over the Gaussian sphere. That Gaussian sphere has a surface area of 4 pi r squared. So I'm just going to say E of R times 4 pi r squared. That's my left-hand side. Any questions on that? No problem, Richard. All right, now we're going to do the right-hand side, which, remember, the right-hand side is where it potentially gets nasty. But in this case, it's actually really easy because we're doing a Gaussian surface that's outside of the entire collection of charge. So we know the total charge is what's Q enclosed. So Q enclosed over epsilon naught just becomes Q over epsilon naught. And left-hand side equals right-hand side easily becomes, and by the way, I didn't write this, but let me do so now. In fact, I think I'll write it in red since I was late on putting it. This is for R greater than big R. Okay. All right. So left-hand side equals right-hand side. That's 4 pi R squared E of R is equal to Q over epsilon naught. And now we go back to our hypothesis. Implies, along with this, of course, that E is equal to Q over 4 pi epsilon naught R squared R hat for, make sure I'm right here so Micah don't bite me, for R greater than big R. Any questions on that? So I'm trying to show that these two facts came together to allow us to figure out that that's the whole vector form of the electric field for R greater than big R. I'm also going to box off this portion. And that's just to keep it separate so no one might might reach the conclusion that that had something to do with solving the problem. It sort of did, but it only had to do with us getting the problem started. So I block that off. Let's go back to the solution now. For, whoa, Nelly. And that's what happens when you leave the automatic neat drawing thing up. So for R less than big R. Okay. So you might think right now, oh, we're going to have to do that thing Mr. Younger just did, where I'm going to set the two rows equal to each other, at the row being Q over the volume. But no, I don't do that, strictly because I just finished showing you guys how we reached the conclusion that every bit of charge on the conductor will be on the surface of the conductor. So what we get is left-hand side is equal to the closed integral E dot dA, which you all know is just going to be 4 pi r squared E of R. Notice that has nothing to do with where the charge is or anything. That's just based on my hypothesis that the electric field is a function of R and R only and points radially outward. Not knowing exactly what the magnitude E of R is, if I integrate that over the surface area of this Gaussian surface, the little black sphere inside, then I'm still going to get 4 pi r squared times E of R. Okay. Speaking of which, it probably wouldn't hurt to go. Okay, so those are two Gaussian surfaces. Now I'm going to do the right-hand side. The right-hand side is the total charge enclosed in the Gaussian surface over epsilon naught, but the total charge enclosed, according to the black boxed off area, is equal to 0. So I get 0 over epsilon naught, which is just 0. Then I can say left-hand side equals right-hand side, and now things really get easy because I've got 4 pi r squared E of R is equal to 0. So E is equal to 0 for R less than big R. And I think I remember to do it right this time. So any questions on that one? All right, now I'm going to graph this and show you something really cool. Okay, hopefully you'll appreciate its coolness. So I'm going to go ahead and graph this, and that's going to be my y-axis, and that, of course, is the electric field strength. Whoa, Nelly. This is going to be my radius r. That's going to be the radius big R. And in fact, what I'm going to do is put this right here, and this quantity is going to be Q over 4 pi epsilon naught r squared. But now the electric field strength is going to be completely 0 from R equals 0 to big R. And then it's going to rapidly jump up and then decline rather rapidly according to 1 over R squared. So that's the actual graph of the electric field for this charge conductor. Notice again, here comes the fun part. Notice here we have a discontinuity. Meaning that part is discontinuous. The electric field, if you take the limit from the left-hand side of the electric field as R approaches big R, you get 0. If you take the limit From the right-hand side, as r approaches big R, you get q over 4 pi epsilon naught r squared. They're not equal, ergo they're not continuous. So the discontinuity is, and notice I got that q over 4 pi epsilon naught r squared by just substituting big R for little r in the equation for E for r greater than or equal to r. So in this case, I can't actually put greater than or equal to. And in fact, I technically have to put a open circle there. Okay. So this discontinuity is in fact going to equal E from the positive side minus E from the negative side. And of course, E from the positive side, dang it, son of a, is Q over 4 pi epsilon naught R squared minus 0. So we get that the discontinuity is Q over 4 pi epsilon naught. Oops, it's supposed to be big R squared in both cases. So let me pull this over here. And let me pull this over here. Now I'm going to do some trickery, some tomfoolery, if you will. I'm going to write this as Q divided by 4 pi big R squared. And then I'm going to divide all that by epsilon 0. And I'm going to ask you all, what is that quantity? It might help you if you think about the units. Anyone? It's not the electric field because it's missing that key epsilon 0 at the bottom. What are the units of 4 pi r squared? Anyone? Bueller? Bueller?
The meter squared?
Meter squared, exactly. And of course, the top is coulombs. Do we know of anything that has units of coulombs per square meter? How about this little guy? So do y'all see that the top is actually the surface charge? Remember, the surface charge density is supposed to be coulombs per square meter. And you can see that total charge is in fact just Q. And the surface area of that sphere is 4 pi r squared. So this is clearly Q over A. And that's what we called sigma. And just like I told you before in the very first problem, the discontinuity is always supposed to be the sigma over epsilon naught if there's a surface charge. Anybody have any questions about that one? So I'm going to say, again, perpendicular component is not continuous if there is a surface charge. Okay. The Q was the total charge. So that was the total charge of the spherical conductor. All right, now I'm going to do one more sphere. Now you've had experience with a actual cylinder. That was the first problem we worked, where I got lambda over 2 pi epsilon naught r times r hat for the vector. In that case, it was r hat cylindrical, so I subscript it with a c. In that case, it's not the same r as we're using here, but if you imagine always at any point, you take and draw a line that's perfectly horizontal from that point to the z-axis, then the r hat sub c will be parallel to that line, but point away from the z-axis. No problem, Brandon. Yeah, go ahead. Since class is almost over, go ahead and everybody chat me your first and last name so I can use that as a role. I appreciate that. I'm going to go ahead and do one more spherical problem. Remember, the rule is you really only have, and I don't know why the screen keeps showing this. Oh, I know, I probably did something through Zoom. But anyways, there's only 3 symmetries that work for you to solve for the electric field. It's got to be a plane that is approximated as infinite, a cylinder that's approximated as infinitely long, or a sphere. Those are the only 3 sort of shapes you can use to calculate the electric field from Gauss's law. So now this time I'm going to say a sphere has a total charge, oops, Q, and a radius R, and its charge is distributed such that rho is equal to K times R squared, where K is a constant. So A what is K? B, what units would K have? And C, what is the E field it creates? Okay. So let's say solution. We know Q is equal to the integral of rho dV. And I'm going to go ahead and draw a coordinate system over here. There's my x-axis, there's my y-axis, there's my z-axis. I'm going to draw a sphere to represent the shape. Okay. And what I'm going to use for the dV is going to be dang it. Is this little spherical shell right here. if I run out of time, you guys can go ahead and split. Looks like no, I still got 10 minutes, so I should have plenty of time. What I'm going to say is this particular radius to the inside is R. That's actually supposed to be to the inside, goober. Hopefully I can erase this. Probably not. Oh, of course not. Okay. Now I'm going to try to draw this back. That's not too bad. Okay. I'm also going to say that this thickness is dr. Okay. It's a sphere. So what I'm going to do is I'm going to write the integral of k times r squared, and then my dv is going to be 4 pi r squared, because that's the thickness of the inner surface. And in some sense, if I multiply, excuse me, that's the surface area of the inner surface. If I multiply the surface area of the inner surface by the thickness, I should have something that looks a lot like the volume, and that's what I'm doing. In fact, the reality is that dV should be 4/3 pi, oops, r plus dr cubed minus 4/3 pi r cubed, like that. But if you carry out that, you'll find that it's essentially 4 pi r squared dr plus terms of the order of dr squared and dr cubed. Okay. So in the Riemann sum, we're going to take basically a limit as the dr gets infinitesimally thick. Therefore, the dr squared is going to be nothing and dr cubed is going to be even less. So that's why we don't have to actually do that. So now I can write this in as 4 pi r squared dr and basically get 4 pi k times the integral of r to the fourth dr, and I'm going to integrate that from r equals 0 to big R, because as I said in the original problem, the radius of the sphere is big R. So when I compute that, I get 4 pi k over 5 times r to the fifth. That means Q is equal to 4 pi k over 5 r to the fifth, which tells us that k is actually supposed to be 5q over 4 pi r to the fifth power. So that's one answer. The other answer is, what's the units? Can anybody tell me that? Now, the only thing that actually has any units in there is the Q and the R. So I'm going to put the Q up there, and I'm going to put the R up here as well. So anybody have an idea? Yep, that's very good, Micah. That's coulombs per meter to the fifth. Any questions on that? All right, now I'm not even going to take the time to draw the Gaussian surface. And notice I'm saying surfaces because I got to do one for r greater than big R and one for r smaller than big R. So first off, I'm going to say r greater than big R, left-hand side, closed integral E dot dA. You probably all can guess what my hypothesis was. So it's going to be E of R times 4 pi R squared. Right-hand side is Q enclosed over epsilon naught. We know that the total charge is Q, so this is just going to be Q over epsilon naught. So our electric field for R greater than big R is just the typical spherical charge distribution, 4 pi epsilon naught R squared R hat for R greater than big R. In other words, nature doesn't know anything about the charge distribution. All it knows is that is a spherical charge distribution with a net charge of Q. So it just acts like a point charge Q acting at the origin or sitting at the origin. And that's what we're computing here. So notice that happened to be the case with all these parts. For R bigger than R, if the charge is spherically distributed, it doesn't matter at all how it's distributed. As long as it's spherically distributed, it's always going to look like Q over 4 pi epsilon naught R squared for a spherical distribution. Anybody know how to erase these little green lines that Zune's put in there? It's got some way of drawing it. Annotate. Let's see. Oh, I see. There's a whole bar over here. Wow, that's impressive. There's my eraser. Yoo-hoo, got rid of it. Okay, now I'm going to do the other part. Sorry about that diversion. Now I'm going to do for R less than big R. Now, this is again the case where, as you can see, the right-hand side of Gauss's law is where trouble comes in. So the left-hand side, I think you all can realize that that's going to be the closed integral of E dot dA, which is just going to be E of R times 4 pi R squared. And then the right-hand side is going to be a little bit more complicated. So I'm going to take time to write or to compute Q enclosed. So the right-hand side is Q enclosed over epsilon naught, but Q enclosed is actually equal to the integral of rho dV from R equals 0 to just plain R. So that's going to be, since we know the K is going to, well, I'll just go ahead and take the step. I'm going to say that's K R squared times 4 pi R squared dr integrated from 0 to R. This is going to give me 4 pi K times R to the 5th over 5, which I can now put K in. I'm going to have 4 pi over 5. The K we found was 5Q over 4 pi R to the 5th. Darn it. R to the 5th. And then all of this would be times little r to the 5th. So you can see clearly the 4 pi cancels out with the 4 pi, the 5 cancels out with the 5. And what I get is almost exactly like what I did before when I just did a uniformly distributed charge. I'm going to have Q, dang it. I'm going to have Q over epsilon naught times R to the 5th. That's little r to the 5th over big R to the 5th. Now I can say left-hand side equals right-hand side. and this gives me 4 pi r squared E of r is equal to Q over epsilon naught r to the 5th over big R to the 5th. What we see is, dang it. What we see is those two cancels out and just leaves a 3 there. And we get E is equal to Q R cubed over 4 pi epsilon naught big R to the 5th. And this is for R less than big R. Now you can tell if you actually substitute little r for big R, you can actually see that they will be continuous. So I can go back and add that. And that's it. The electric field increases like R to the 3rd power for R less than big R. And then it falls off like 1 over R squared for R greater than big R. And that's it. You guys are free to go. Again, make sure you chat me your first and last name for roll in case you didn't already. And hopefully this helps you. Get a lot of practice. We're going to have a test a week from, I think it's next week. Actually, I got to double check with you guys, but just make sure. Anybody have any questions? See you, Shonda. See, Micah's here. Mitchell's still here. Oh, more people falling off. That looks like it. Bye, everybody. Bye-bye. Thank you for coming. Oh, did y'all see my mini moods of Tita? Mini moods of Tina. Oh, man, my Zoom is automatically fixing it. I hate it when that happens. Oh, well. Have a good one, everybody. Bye-bye.